Okay, this is your Chapter 3 introductory video. This is a difficult chapter conceptually, and I'm not going to attempt to try to, in this video, cover the entire chapter. A lot of these concepts will be new to many of you, and many of them are difficult conceptually. My goal here is to create a kind of environment in which you can start to grasp the material and start to feel comfortable in class with some of this. So I'm going to really attempt to just go through the earlier part of the chapter. This is atomic structure and explaining the properties of elements. This is where an an a atoms focused approach comes in, is where you introduce this concept very early in the Gen Chem 1 and then in your general chemistry sequence. So here are your learning goals for the chapter, and the first three are highlighted in red because that's about all I'm going to attempt to address in this video. In fact, the first one I actually will not address, and we'll save that. We're saving all the calculation type stuff um, for class. I will talk about the electromagnetic spectrum, but I'm not going to talk a lot about I'm not going to talk at all about wavelength, frequency, and energy. I'll talk about the photoelectric effect, and I'll talk about Bohr's model of the atom, which is part of what this is here. And I'll just come up a little bit to write about where quantum numbers come in. I won't really talk about the outcomes of how this is important and why we need it in general chemistry until we get into lecture. Okay, so the first thing I need to expose you to is the electromagnetic spectrum. And for a lot of people, you've seen this before, you've talked about it, but maybe don't have the greatest understanding of it. So the way this is structured up here, the electromagnetic spectrum includes several things that you will see that are familiar to you. Microwaves, right? Ultraviolet. And here, of course, is your visible light. And this is the visible light blown up down here, showing you the range of wavelengths. So what we're looking at here is wavelengths in meters right here. This scale down here is nanometers, the blown up scale from 400 to 750 about. There's no discrete boundaries, but that's roughly about where it runs. Some people say 400 to 800, some people say 380 to 780, whatever. It's in that general range. And it's wedged right between ultraviolet and infrared. And the way to remember this too is that the red end of the spectrum, of the visible spectrum, is right next to infrared, and the violet end of the spectrum is right next to ultraviolet. And you see we're going in wavelengths here, and the wavelengths are getting larger as we move left to right. We're up to 10 to the 4th down here. We started at 10 to the minus 16th, so these are larger wavelengths. So 750 nanometers is larger than 400 nanometers. The other thing that's shown here is frequency, and frequency actually is increasing in this direction. You see this arrow here showing you frequency is increasing in this direction. Over here it's 10 to the 24, down here it's 10 to the 4. Frequency is, if you will, the number of oscillations per second. When you think about a wave being looking like something like this, right? Something like this would have a higher frequency. More oscillations per second if these both represented a second. So down here is high frequency. Down here is low frequency. And what you notice is down here you've got things like gamma rays and X-rays. These are high energy rays that are somewhat more dangerous, right, compared to things like radio waves and microwaves at this end. So at this end of the spectrum we have long wavelengths and so large wavelengths, small frequencies. Down here we have short wavelengths, high frequencies. And you should correlate, and we'll learn this in class, frequency with energy. Higher the frequency, the higher energy. You can see this as being kind of really high energy, if you will. Think about taking two ends of rope. You're holding one end, your friend is holding the other, and your friend starts shaking that rope vigorously. That would be high frequency, right? Or if they just do one little flip of the wrist, if you will, that would be low frequency. Okay, and let's move on to the planetary model, the atomic model. This is what a lot of us learn in high school. If you took a really good chemistry course in high school, maybe AP chemistry, maybe you talked about the quantum mechanical model. In this model, basically, what we're looking at, and this is the one that came out of Rutherford's experiments that we did all back in chapter 2, is basically something that looks like this, right? We've got a atom represented by that. Here's my nucleus. And in the middle of that nucleus, you've got your planetary model. So in the middle of that nucleus, you've got your protons. And of course, you also have neutrons. And outside, you've got your electrons. Orbiting around the center of the atoms. There's problems with this model. And one is that when an object is orbiting another object, it experiences an acceleration. This is kind of classical physics. Velocity has direction and magnitude. The particle is changing direction, which means accelerating. Also, it doesn't change speed, but it is accelerating. It accelerates but then gravity pulls it back in. So, attraction due to the nucleus, it should, based on classical physics, continuously emit electromagnetic radiation, which it does not. This is one of the problems with the planetary model, and what led us to understand that the planetary model was problematic. So there's predictions that are basically completely wrong from classical physics about atoms and what we know about atoms, electromagnetic radiation from classical physics. So that's where quantum theory is going to come in quantum mechanics. Ultimately, a successful model that comes out of this is the Bohr model. And then even the Bohr model gets, if you will, expanded upon and supplanted by a more advanced model that does a better job than the Bohr models. That's just the nature of science. So one of the things scientists had experimented with and things they were doing, we're looking at things that are called emission spectra and absorption spectra, and they would heat certain types of materials up until they glowed and were incandescent. And basically what it came down to is that classical physics was unable to explain the data and the observations that the scientists were seeing when they looked at things like the wavelengths that were being emitted and the energies and at which temperatures we were seeing these and what range of wavelengths they were seeing. None of this stuff could be explained by classical mechanics. This goes into something called the ultraviolet catastrophe. Your book has a figure, doesn't really use that term, but touches on this. You're not really responsible for really understanding, what the problems were with classical physics. That gets beyond this course. If you take physics, they'll cover this in a little bit different way, and you'll get some more details on that. What you're looking at here in this figure is spectra where, like the hydrogen atom, when it gets excited, you put it into like a tube and apply electrical voltage to it, and you look through a particular instrument, you can actually see these colored line bands that you're seeing here for hydrogen, and it's specific for hydrogen. No other element looks like this. And no matter what your source of hydrogen, you're always going to see this. And here's one for helium and one for neon. Scientists didn't really have any idea why we were seeing this. First person to come along, really, and you'll see this in the lecture, we'll talk about this in your book, is Max Planck. And what he basically said was that, atoms kind of absorb and emit energy in discrete packets, not in a continuous energy absorption and emission. So the difference here is between a ramp. This would be the way classical physics would have viewed it, as a ramp, the way atoms would absorb and emit energy. But Planck comes along and says, no, it's actually in these discrete steps. And things like this are not unique to science. I mean, the steps in themselves are what we call discrete, and they're what we call quantized, and that is you have enough energy to get up to the first step. If you don't have enough energy to get up to the second step, your leg's not going to go up, right? And you're not going to use any excess energy to get up to the first step. You're simply going to step on the first step. This is what we call quantized, discrete energy states. A lot of people would have thought, okay, you take this piece of metal, you heat it up, and it absorbs a continuous amount of energy. You heat it a little bit more, it continues to absorb a particular amount of energy, and that's the way you get this continuous absorption and emission of energy. That's been shown not to be the case for a lot of these for atoms within materials. So this is not unique. We see this all in nature. I mean, if a chicken lays eggs, it's going to lay 1, 2, 3 eggs. It's not going to lay 2.5 eggs. So, if you will, biology is quantized in that sense in terms of reproduction. Okay? You don't have a continuous spectrum of possibilities for numbers of eggs to be laid. They are discrete numbers. There's lots of numbers between 1 and 2, but you can't lay any eggs that result in something between 1 and 2. So this concept is not entirely new. Something else you'll read about and we'll talk about in class is the photoelectric effect. And this is Einstein's work. And this basically says when light shines on metal surface, that surface can emit electrons. And this can actually be measured. And you can actually create a current. And we use this all the time now. Any sort of light meter, of course, you know, solar cells now and solar energy is all based on this. But there's lots of other things, your calculators and all that, lots of different electronics and switches, automatic door openers in supermarkets. You know, you pass in front of that door, you block the light, or that pass in front of that path, you block the light, that triggers the switch to open up the door. So this was a concept that Einstein came along to say, and what he described it as is one of the keys, taking Planck's ideas. He had said basically light previously had been known simply as a wave. Well, he's saying actually that wave is composed of photons, if you will, light particles. And that was the only way to explain what they were seeing, because we'll talk about this in class. Some of the results they were seeing didn't make sense with classical physics describing it as a wave. It had to do with the intensity of light and the point at which you actually see these electrons emitted. They don't get emitted under any conditions. So there are specific conditions. And Einstein explained it as these photons within the light were actually hitting the electrons and dislodging them. And he needed that idea from Planck, this discrete idea. So you didn't have this continuous, if you will, wave of energy. You had individual particles within that wave that actually contain the energy of that particular frequency of light. So that was a groundbreaking idea. So ultimately we come along with this Bohr model of the atom now. And while it looks very similar to the planetary model, what we have is these orbits here, and these are now these discrete energy levels. So an electron can exist in, you know, an n equal 1 level, an n equal 2 level, n equal 3, n equal 4, n equal 5. It can't exist in between. So you can see the idea now here. An electron has discrete energies. Okay? There's not a continuous possibility for where the electrons can reside, and because they're in these discrete energy levels, almost like peeling layers of an onion. You have a layer, you peel another layer. There's nothing in between. There's no layers in between. So this is very similar to that concept. This was Bohr's model of the atom, and it wound up being similar to like a ladder, if you will. N equal 1 being your ground state, if you will, your lowest energy, and these being higher and higher energies. Also, further and further away from the nucleus as you move up. So this would be close to the nucleus, and this would be further from the nucleus up here. And he was able to, you know, characterize these as having specific energy. So what we see now here is, in fact, hydrogen has a single electron, right? When you look at your periodic table, we talk about that. It has one electron. In its ground state, that electron will exist in the n equals 1 orbital right here. Its lowest possible energy state, can't get any lower. It can then absorb energy, like by a photon that comes in. It can absorb that energy and excite now up to, say, n equals 2. It's now in the excited state. When it comes back down, which it ultimately will, what goes up must come down, right? It's going to come down to a lower energy of state, similar to relaxing, the way you would relax at the end of the day, release that energy, comes down to a lower energy state. What we have now is back in the ground state. Well, what's interesting is that Bohr's model now, if I take a look at these 4 lines right here, these exactly explain, sorry, I'm going to go back up here. These exactly explain these 4 lines right here, which is what's amazing. Okay, so here's the idea. The electrons, now imagine you have a bunch of hydrogen in a tube and a bunch of electrons all becoming excited, some excited, more than others, some not excited. So you have the whole, if you will, distribution of possibilities. What we're seeing here now is when you get electrons going from the n equals 3 energy level to the n equals 2. So now I talked about it being excited to n equals 2, but you can be excited to additional energy levels. So we go back here, there's nothing to keep an electron that's in n equals 1 from absorbing a photon and exciting all the way up to n equals 5. Just has to have the right amount of energy. That's all. Okay? So what we're seeing here then is this produces a particular color. And these colors right here, and I've colored up the colors, so I'm going to do away with that, actually correspond to the colors in this diagram. This violet one represents this line that they saw back here, right here. Okay? And the next one represents the next line over and so forth. So the idea here is this one is the most energetic. Whoops, I'm on the eraser here. That's the problem. This one's the most energetic, so it represents violet, which is more energetic. This one is red, least energetic. Why? Well, it's only going from n equals 3 to n equals 2. No different than walking steps, no different than dropping a ball from different heights. The key here is that an electron absorbs energy, it goes to a higher energy state, and then it emits it when it comes back down. It will emit the exact same frequency of energy, the exact amount packet of energy that it absorbed. So that's the key with this absorption and emission. What you're looking at here is emission. So de Broglie came up with this idea that, wait a second. If Einstein showed that, radiation has these particle characteristics, maybe particles like electrons behave like waves. And that's exactly what this experiment is about. And this is kind of complicated. It's not in your book. It's not something you really need to know for this class. But it's interesting, and I like to cover it for those students that really are trying to get a handle on this. But don't get frustrated, because Richard Feynman is famous for saying nobody truly understands quantum mechanics. And that is the case. There's no analogies to be drawn to it, so it's very difficult to conceptualize. Things on a very small level simply do not behave like they do on a large level. So electrons do not behave like a planet orbiting a star or a billiard ball on your pool table. They behave very differently. So we have this is the famous double slit experiment. There's been tons of double slit experiments. You can Google it. You can watch Khan Academy. You can watch YouTube videos. So this is a machine gun on the top here. And let's say this machine gun is spraying bullets. And you have 2 slits in this wall, this partition, and a screen over here that actually detects where the bullets hit. Well, this is what you would get. What you see here, probability-wise, most of the bullets are coming straight through from this one right here. You get a high peak, and that's what this curve represents here, that slit. And this curve represents this slit here. You pull them together, you actually wind up with this, because you've got this point here where they both have a probability. Remember, because they can do things like this, and they can hit here and go like this, so that's why you're getting this spray. Well, you would expect electrons to do the same thing, and in fact, they do not. They give you a pattern like this, and the only way to explain this pattern is by waves. And if you've had physics, and you can look at this and understand it, but if not, you're going to need to wait for your physics course. But waves, like water waves, similar, you can use that as an analogy, behave very differently. When they come through this slit, they're going to do this, and this one's going to do this, and they actually interfere with each other, and both constructively and destructively. That's why you get this pattern here. And this is what we see when we fire electrons, which means the electron has wave characteristics. And what we're seeing now is that light has both wave and particle characteristics, and particles that are small, like protons, electrons, neutrons, have wave characteristics. In fact, everything has wave characteristics. But big objects like baseballs and things like that, we can't detect those waves because the wavelength is so small. Okay, so then we have Heisenberg's uncertainty principle, and basically what he showed is that it's impossible to take any measurement of an object without disturbing it. Now, what you need to understand is this is not somehow a limitation of our instrumentation that somehow will overcome it eventually. That's a common misconception. No, this is the very nature of the fact that in any sort of observation, whether you're viewing something with your eyes or with an instrument, observation requires interaction of some sort of electromagnetic radiation with the object. For you to see a ball in a dark room, you shine the flashlight on it. That's the interaction of the electromagnetic radiation that allows your eye to see that. The problem is with very small objects, like an electron, as soon as you detect that electron with some sort of electromagnetic radiation, it changes the electron's path and it changes its speed. Because it's so small, it's affected by it. The ball in your room is not affected by it. This is what this figure is trying to show you. As soon as that photon is used to detect that electron, it's now moving in a different direction with a different speed. You can see the problem. You can't get around this because you need electromagnetic radiation to interact with something. And you might say, well, just use a less energetic electromagnetic radiation that won't disturb the electron. The problem is the less energetic ones have really large wavelengths, and you can't use those to detect an electron. You need something with a smaller wavelength. And I'll talk about microscope resolution in class that'll help explain that. So ultimately, you get to people like Schrodinger and the development of quantum mechanics and the math that goes along all with this, and the development of all the quantum numbers and the ability to apply things beyond hydrogen, to apply things to something beyond one electron. And that's what Schrodinger's work did, and all the equations he developed leads to basically quantum numbers. And the quantum numbers, a series of quantum numbers, the n you saw in the Bohr equation, or the Bohr explanation of his model, is one of the quantum numbers. But we're going to add two others, and ultimately we'll add a third one in class. But basically, these quantum numbers are basically addresses for where the electrons are. What we're now looking at is the probability of where to find the electron, no longer exact positions. So while I can tell you exactly where the Earth is at any moment surrounding the sun as it moves, but as it moves around the sun, physicists can predict exactly where the Earth is going to be, a year from now. You can't do that with an electron. You can only talk about probabilities. That's really what comes out of quantum mechanics. So ultimately, just to summarize, we have classical theory. This is classical physics. And some of the work they did from radiation from hot metals. Max Planck took this along with Einstein's photoelectric effect, and we said basically energy is quantized. We looked at things like line spectra and Bohr, coming up with the hydrogen model. This is the matter waves. This is the double slit type stuff. The matter has waves also. And ultimately, with Schrodinger and Born, we come to radiant energy and matter have both particle and wave properties. This is quantum theory, and the math that goes along that is quantum mechanics. And this concludes the video. You will need to do some reading in this class to just put your mind at ease. But once again, don't kick yourself over this, because as Richard Feynman is famous for saying, no one truly understands quantum mechanics.